The purpose of this exercise is just to kind of combine the stoichiometry that you have previously learned with the molarity that we have been learning. As a reminder, molarity is a conversion factor, just like molar mass is a conversion factor. So we're looking at moles per liter. And in any stoichiometry problem, we're looking at equations. So the whole idea is if you can take the information you're given and get to moles, then you can do the stoichiometry that you have gotten really good at. So in this first problem, we're looking at excess sodium hydroxide solution added to 20 milliliters of a 0.184 molar solution of ZnCl2. And we're going to calculate the mass of zinc hydroxide that is predicted to precipitate. So we're given a volume and a concentration for one of the reactants, and then we're looking for the mass of product that is going to precipitate. So like in any problem, I would encourage you guys to first write down what you actually know underneath the reactant and product that you're looking at. So information we know is that we have 20.0 milliliters of a 0.184 molar zinc chloride solution, and then we also are looking for grams of zinc hydroxide. All right, I know using the concept of molarity that if I were to take and look at the volume and the molarity, I can get the number of moles, right? Moles is equal to the molarity times the volume. Another reminder when you're working with these is to transfer the milliliters over to liters. So as you watch this video, you'll see a lot of times I've already done that step. All right, so the first thing I would do is I'm going to take that volume of 0.02 liters and put it over 1. And the next thing I will use is that molarity conversion factor. So I know that for every 1 liter of zinc chloride, I have 0.184 moles of zinc chloride. That's giving me how many moles I need. So my next step would be to do a mole to mole ratio. And when I look at the moles of zinc chloride to the moles of ZnOH2, I notice that I have the exact same, it's a 1-to-1. And then in the next step, I need to figure out how many grams of zinc hydroxide I have. So now I can use the molar mass. So 1 mole of zinc hydroxide is going to be 99.4 grams of zinc hydroxide. I'm going to go back in and do one really quick thing here because I noticed in my edits I was missing a few things. And so then when I go to calculate that out, I'm going to get a final answer of 0.366 grams of zinc hydroxide. All right, in problem number 2, we have a new equation. This one has also been written out for you and balanced beforehand, which is always nice. We're looking at how many milliliters of a 1.5 molar solution of hydrochloric acid would be required to fully react with a solution formed by dissolving 0.775 grams of sodium carbonate. And so in this one, again, we're going to just mark down what we're given, the thing that we're looking for, and then look to see how we can solve this. In this case, what I'm going to have to do is start off with that sodium carbonate and figure out how many moles of sodium carbonate I have, and then do a mole to mole ratio to the hydrochloric acid. Once I know the moles of hydrochloric acid, I can use that 1.5 molar conversion factor to get to the liters, and then from liters I can get to milliliters. So just kind of working that out, showing the stoichiometry. We're going to do 0.775 grams of sodium carbonate over 1, and then we're going to go ahead and take and divide by the molar mass of sodium carbonate, which would be 105.99 grams. This tells me how many moles of sodium carbonate I have. The next step is comparison moles to moles. So 1 mole of Na2CO3 is 2 moles of HCl. And now I can use my conversion factor of 1.5 moles of HCl per liter. And the last thing I need to do is convert from liters to milliliters. So I know there's 1,000 milliliters in 1 liter. All of my units should cancel out, and I should just be left with milliliters at that point of hydrochloric acid. And then 3 significant figures would be 9.75 milliliters of HCl. In problem 3, I am given the volume and molarity of barium nitrate and I'm being asked to solve for the grams of barium chromate. So starting off by writing those out, double checking to make sure that everything's balanced. It's looking pretty good there. So again, I'm going to look at what information I have. I'm given volume of barium nitrate in milliliters, so I'll convert that to liters, and then I'm also given molarity. So if we go molarity times volume, that will give us moles. I'm going to show you again the stoichiometric method for that. So always starting off with my volume over 1, and then I will use my molarity as a ratio. So I know I have 0.424 moles of barium nitrate per 1 liter of barium nitrate. I'm now in moles of barium nitrate, so I can again go to the equation and do a mole to mole comparison. I know that there's 1 mole of barium nitrate for every 1 mole of barium chromate, and I'm 1 step away from my answer. Once I know moles of barium chromate, I can convert using the molar mass of barium chromate, which is calculated to be 253.30 grams. And at this point, all that's left to do is plug that into my calculator, which would be 0.05 times 0.424 times 253.30, and I get an answer of 5.37 grams of barium chromate. In the next problem, it's asking us to determine the number of milliliters of a 0.246 molar silver nitrate solution that would be required to precipitate all of the phosphate ion in a solution containing 2.1 grams of sodium phosphate. So again, questions like this can seem confusing at first. Let's start by listing out what we know. The first question is, or the first thing that we know is we're looking for milliliters, and we know the molarity of that silver nitrate solution. And the other thing we know is that we have 2.1 grams of sodium phosphate. Now, it's asking us to make sure that we can precipitate all of the phosphate ion in the solution, and here's kind of a nice little trick to do there. First, I want to look at sodium phosphate, and I want to break it down into its specific ions. So I have 3 sodium ions and 1 phosphate ion. What I have there is a 1-to-1 mole ratio. So whatever I have in moles of sodium phosphate, that is how many moles of phosphate ions I have. It's always good to double check this because it's something else that could need to be added to a calculation. In this case, it's 1-to-1, so I'm going to treat my sodium phosphate like it is my phosphate. So again, I know that I have 2.10 grams, and I'm going to go from sodium phosphate over to silver nitrate. So I'll start by writing that 2.1 grams of sodium phosphate over 1. I will then look at the molar mass, which is 163.94 grams, and then I'm in moles of sodium phosphate. Now I can compare to silver nitrate. I have a 1 mole of sodium phosphate for every 3 moles of silver nitrate. And then the next step I can look at is looking at the molarity. So I know that I have 0.246 moles of silver nitrate per 1 liter of silver nitrate that I'm getting from that molarity. And then I need it in milliliters. So I'm going to just do that one last conversion, which is taking 1 liter has 1,000 milliliters in it, and go ahead and plug that into the calculator. And the final answer should be 156 milliliters of silver nitrate at a concentration of 0.246 molar would be required in order to fully precipitate out all 2.1 grams of sodium phosphate's phosphate ions. Question number 5 introduces the concept of molar volume. And so as you can see towards the end of the problem, it states that the molar conversion for gases under standard conditions is 22.4 liters per mole. Essentially what that is that all gases will occupy 1 mole of any gas will occupy a volume of 22.4 liters under certain conditions. And for the last 3 problems, that's what we are going to assume is that things are happening under standard conditions. In this problem, we're looking at what volume of SO2 is required if you're going to take 35 milliliters of a 0.924 molar solution of sodium sulfite and go ahead and run that to completion. You're assuming that the sodium hydroxide is present in excess, so really the sodium sulfite will be your limiting reactant. So again, we want to figure out how many moles that is. So first start by converting your 35 milliliters over into your liters. So you have 0.035 liters, put that over 1, and then use the molarity, moles per liter, to do your next conversion and cancel out liters. Once you have that, you're now in units of moles. So this is the time to look at the actual mole to mole ratio in the equation. We have 1 mole of sodium sulfite for every 1 mole of sulfur dioxide gas that's made. And then from there, we're in moles of sulfur dioxide gas. So from here, we can actually use that molar conversion of 22.4 liters per mole. We'll put 1 mole of sulfur dioxide gas in the bottom and that 22.4 liters of SO2 on the top. Plug that into your calculator. Really, all you're doing is multiplying everything across the top, and everything on the bottom was a 1. And your answer should be 0.724 liters of SO2. In problem 6, we're given the information how many milliliters of a 6.2 molar solution of sodium hydroxide must react to release 2.4 liters of hydrogen gas. So if we look at this and kind of just identify the variables that we know, that 2.4 liters of hydrogen gas as the product is what we know for certain. So we will actually start with that and put that over 1. And from there, we're going to use the molar conversion of 22.4 liters per mole to get how many moles of hydrogen we have. From there, we can actually use the coefficients in the equation, and we have a 3 to 6 ratio, so 3 moles of H2 on the bottom and 6 moles of sodium hydroxide on the top, and now we're in units of moles. So the next thing we can do is go from our molarity of moles per liter to get our volume. And then this particular question asks for milliliters of sodium hydroxide. So from there, we'll use the conversion that 1 liter of sodium hydroxide has 1,000 milliliters. Again, multiply everything across the top. And on this one, we're going to have to do a little bit of division. Make sure that you're either putting that in parentheses, hitting like divided by, and then putting parenthesis 22.4 times 3 times 6.20 and another parenthesis, or take your answer from the top and individually divide each of those answers by the numbers on the bottom. When you do that, your answer should be 34.6 milliliters of sodium hydroxide. All right, for this last problem, we're looking at a question where we are trying to identify the volume again of sodium sulfite if we know the molarity, and we also know the volume of SO2. So writing those variables down, something to remember is that when we're looking at volume, the conversion factor for volume of gases works under standard conditions. So it is important that the problem lists that out. And then the other thing is it's in liters, not milliliters. So make sure you're converting those 350 milliliters over to 0.350 liters to start off with. And I would start with the product on this one and then go over to the reactant side because that is what we're looking for. So 0.350 liters of sulfur dioxide gas over 1. Let's use that molar conversion of 22.4 liters per 1 mole. That gives us moles of sulfur dioxide. We'll do a mole to mole comparison for our next step to get to moles of Ne2SO3. And from there, we'll use the molarity of 0.92 moles per 1 liter. And that's going to actually give us volume in liters. And from there, we could also say, like, it didn't specify what volume units you needed. So you could leave it as 0.0169 liters or multiply that answer by 1,000 to get 16.9 milliliters.